I am Dr. P.S.V.Shanmukhi, Associate Professor, Department of Physics, Aditya University. Now, I am going to explain about the density of states in case of the conductors. At the end of this lecture, student will be able to understand the energy levels of free electrons, how the electrons are distributed among various energy levels, and he can also derive the density of states of electrons. Coming to, suppose the free electrons are distributed among various energy levels. This is the energy band diagram of a metal. There are so many energy levels like this. Each energy level can be occupied by maximum 2 electrons. One is clockwise spinning electron, second one is anti-clockwise spinning electron. Like this, each energy level can be occupied by 2 electrons maximum. Okay, how many states are available, how many states are occupied by the electrons, that what we can understand. Here, the density of states is defined as the number of energy states available from the energy E to E plus dE. Means in the energy range dE, how many states are available to be occupied by the electrons. For that, say the density of states, it is actually given by Z of E dE. From the energy E to E plus dE, the density of available energy states, it is given by Z of E dE. Like this it is written. Of course, generally it is given by pi by 2 into n into or n square dn. The density of available energy states is given like this, but we don't know what is the expression for this n or dn, all those things. We can get them from the energy levels. Actually, in case of one-dimensional potential well or potential box, the energy levels are given by E is equal to n square h square by 8 m L square, where L is the width of the potential well or the side of the potential box. N square h square by 8 m L square, h is the Planck's constant. Now, rearranging the terms, we can write n square is equal to 8 m L square by h square into E. And from that we can get n expression. N is equal to under root of the above one, means 8 m L square by h square whole power 1 by 2. That is n. Okay, once again from this n square, let us take the variation. Differentiate that one. What we get? 2n dn is equal to 8 m L square by h square is a constant term. Energy is a variable in this one. We get dE. So, from that what is n into dn? The n into dn is equal to 1 by 2 into 8 m L square by h square into dE. Now, we got this n into dE and also equation 6, that is n expression. So, generally the density of available energy levels, it is given by pi by 2 into n square dn or n into dn. Substitute these two in the above equation, we get Z of E dE, it is equal to pi by 2 into 8 m L square by h square whole power half, that is n e power half into half 8 m L square by h square into dE. Okay, something we are getting, and simplifying this one, we get this as pi by 4 into 8 m L square by h square whole power 3 by 2 e power half into dE. So, we are getting some equation there. Actually, you just observe this diagram. Each energy level can be occupied by maximum 2 electrons. As per the Pauli's exclusion principle, each energy level can be occupied by 2 electrons. One is the clockwise spinning electron, another one is the anti-clockwise spinning electron. Of course, each electron has its own energy state. That means one level corresponds to 2 energy states. One energy level can be filled by 2 electrons. Each electron contains its own energy state. That's why I want to write about the density of energy states now. Again, it is also denoted by Z of E dE. So, it is multiplied with 2. Actually, number of available energy levels, it is given by pi by 2 into n square dn. On simplification, we got this equation number 8. Now, how many available states are there? That is multiplied with 2 now. 2 into some previous expression. On simplification, we got this equation number 9. That is pi by 2 8 m by h square whole power 3 by 2 e power half into L cube dE. These are the number of available energy states in the energy range dE. Means from the energy E to E plus dE. Means in the energy range dE, how many states are available? But I want to get the expression for density. Density means per unit volume. Per unit volume, how many energy states are available? The number of available energy states per unit volume means divide with V now. What is volume? Actually, it is taken as a potential well of length L. Otherwise, you can take it as a potential box of side L. Say this is a 3-dimensional potential box. Therefore, what is the volume of this one? Volume is L cube. That's why dividing equation 9 with V means L cube. L cube will be cancelled and get this expression as Z of E dE. It is equal to pi by 2 8m by h square whole power 3 by 2 e power half dE. That L cube is cancelled. So, on simplifying this one, we are getting the expression. Observe this one, Z of E dE is equal to 4 pi by h cube 2m whole power 3 by 2 e power half into dE, where E is nothing but the energy. In general, we take this as the kinetic energy also. Only the free electrons are having only the kinetic energy. This is the expression for the density of available energy states in the energy range E to E plus dE or in the energy range dE. Simply one thing. Actually, in a metal, the free electrons are distributed among various energy levels. Each energy level is occupied by 2 electrons. One is clockwise spinning, another one is anti-clockwise spinning electron. So, one level is equal to 2 states. Each electron has its own energy state. Okay, how many energy states are available first? For that, the density of states is defined as the number of available energy states from E to E plus dE around the energy E per unit volume. That's what we just take. Anyhow, first we are taking number of available energy levels, and from the one-dimensional potential well problem, the quantized energy value C is equal to n square h square by 8ml square. We are getting n square and afterwards n, and differentiating that n square expression, we are getting n into dn. Substituting this n into dn and that n in the equation number 3, above equation, we get Z of E dE or Z dash of E dE. We are getting like this. These are the number of available energy levels. Then how many energy states are there? One level is equivalent to 2 states. As per the Pauli's principle, each energy level is filled by clockwise and anti-clockwise spinning electrons. That's why the number of available energy states, it is given by 2 into that available energy levels. Therefore, multiplied with 2 here. Afterwards, we get this expression number 9. So, but I want to get the density of states, means number of available energy states per unit volume. Z of E dE, that divided by volume V. So, what is volume? Where L is the side of the box or length of the box, then L cube is the volume of the box, potential box or potential well, no problem. Then dividing with L cube, finally we get Z of E dE is equal to the final expression 4 pi by h cube 2m whole power 3 by 2 e power half dE. This is the expression for density of available energy states. So, in this article, coming to the summary, we have discussed the energy levels, distribution of electrons among various energy levels, and also we have derived the expression for the density of available energy states. That what we have seen. Thank you.